Alright, the next topic now is not about how to make lunch, although it might look it. What we have here is a picture of a tray of food. It's getting me hungry. Looks like we have a lot of deli stuff. I can see some tomatoes, and I don't know what this stuff is here, but this looks like it might be turkey. We have some cheese, plenty of lettuce, and we have oil and vinegar, it looks like, salad dressing, got some condiments. The question is, I want to make some sandwiches using all this stuff in some rolls, but you notice that I only have 2 rolls? So the number of sandwiches I can make here is really determined by how many rolls I have. If I had 20 rolls, then the rolls wouldn't be determining how many sandwiches I could have at all. So what determines how many sandwiches? Just the rolls. And the rolls then would be called the limiting reactants. So this next topic is really how it happens in chemistry, where we know the amounts of both reactants, never just one. And so what we're going to be seeing is that you're going to be looking at chemical reactions between 2 or more reactants, where the amounts of all the reactants are known, and then we still want to answer the question, how much of the products can I make? What we're going to see is only one reactant will be completely reacted, and that one's called the limiting reactant. If you only have one other reactant, that one is called the excess. That means there'll be some left over of that one. Just like in this diagram here, the excess are the deli meats and the salad stuff. Okay, so let's get into that. So here's a question when you're asked, what is the limiting reactant for the same equation? You might wonder, why am I using this one all the time? That's because it's short and it's easy to write. But here we have our 2 reactants, 2 moles of nitrogen and 4 moles of hydrogen are going to be put together in a container and reacted. Now, will all 2 moles and 4 moles of this react? The answer is no, unless the moles are in the same ratio as the equation. But the equation says the ratio is 1 to 3. So for every mole of nitrogen, you need 3 moles of hydrogen to completely react it. If our numbers were in that 1 to 3 ratio, that would be fine, but they're not. So how do we figure out which one of these 2 is going to be completely reacted? In other words, which one's the limiting reactant? So what I'm going to do is pick on each reactant separately and answer kind of like the same question. So this first one, how many moles of hydrogen are needed for 2 moles of nitrogen to completely react? So I'm writing my equation again. I'm starting with this, and I'm checking on my hydrogen. So you notice that if I want to react 2 moles of nitrogen, because it's a 1 to 3 mole ratio, I need 3 times this number, or 6 moles of hydrogen. So 2 to 6 is the same as 1 to 3. If I had 6 moles of hydrogen, both of them would be completely reacted. But I don't. I have less. What does that tell me? That tells me that not all my nitrogen is going to react. I'm going to use up all my hydrogen. Now sometimes that can be tough to see. So let's check out the other reactant, and maybe that'll be easier for you. What if the hydrogen were completely to react? How many moles of nitrogen would be needed? Here's my equation again, and here's what I'm starting with. So now I said, if all of my hydrogen is to react, how much nitrogen is needed? So you notice it says 3 to 1, 4 to what? So in order for me to figure out what that what is, I'm going to take my number 4 and divide it by 3 and see what I get. So a 1 to 3 mole ratio would be the same as 1.33 to 4. So these 2 are in a 1 to 3 mole ratio. So you can see easily now, if I started with 2 moles of nitrogen, I'm only going to use up that much. That means I'm going to have 0.7 left over, in excess of 0.7 moles. I'll have no hydrogen left. All of it will be reacted, and that's going to be my limiting reactant. And as far as how much product could I make, if that was asked, it's the limiting reactant that determines it. Once all the hydrogen is gone, the reaction's over. There's another way to do this. I'm going to show you the easy way. Now the easy way is to answer the question, how much product can I make? So I'm going to ignore this question in the beginning. So my product is ammonia. So what I'm going to do is I'm going to take each of my reactants separately, figure out how much ammonia each one could produce if they were completely reacted. I'm going to get 2 different answers. Only one answer can be correct. So let's see the solutions now. For all of my nitrogen to react, it'll react in a 2-to-1 mole ratio. See the 2-to-1. And I could make 4 moles of ammonia. If all of my hydrogen were to react, here's my ratio from the equation for ammonia and hydrogen, 2 to 3. I could make 2.7 moles of ammonia. So you notice I have two different answers for how much ammonia could I make. The right one is always the smaller amount. Now, you might wonder, why is that true? Because this is what it tells us. Once you've made 2.7 moles of ammonia, all the hydrogen is now used up, and the reaction ends. So therefore, it'd be impossible to make more once you run out of one reactant. Now, the reactant that makes that smaller amount is the limiting reactant. So we have kind of answered the question, which is the limiting reactant. We just did it, looks like kind of a roundabout way, but it's the simplest way. So this is the way I recommend you do it. Now here's one for you to try. Now we have two different questions, remember. You have 2.5 moles of methane with 4.5 moles of oxygen. Only one of them will be completely reacted. How many moles of water can you make? If you'd like to give it a shot at this point on your own, why don't you just pause, go back later, and check out the solution. So here are my two questions. 2.5 moles of methane, how many moles of water? 4.5 moles of oxygen, how many moles of water? So for my methane, it's going to react in a 2-to-1 ratio with the water. You notice here's the 1, here's the 2. I could make 5 moles of water. Now if I take my oxygen, solve for that, if all my oxygen were to react, I could make 4.5 moles of water. Which one's the right answer? It's always the smaller amount. So that's the answer to the question. And we can do the same thing with grams. Here's my chemical equation now. So now I'm going to make a mixture of 8 grams of hydrogen and 30 grams of oxygen. The answer, the question is, how much water can I make? You might assume, because there's less of hydrogen in grams, that the hydrogen is going to be the limiting reactant. But you don't want to make that assumption, because remember, things are reacting together mole to mole, not grams to grams. All right, so let's see the solution to it now. So again, we're going to make two solutions. One for the hydrogen, one for the oxygen. For the hydrogen, 8 grams of hydrogen would produce 72 grams of water. You see the 2 to the 18, that's 2 times the molar mass, 2 times the molar mass. If we take out 30 grams of oxygen as the given amount, because we are dividing by 32 and not 4, we get a smaller amount. So which one of these two is the right answer? This one. Which was the limiting reactant? The oxygen. So you cannot assume, because the hydrogen was in the smaller mass, that it's going to be the limiting reactant. Now try this one on your own. Let's see how well you can do. Then come on back and take a look at the solution. Okay, here we go. So I break that down into two questions. Again, you might assume now from the last problem that I won't be fooled again, and the oxygen will be the limiting reactant. Let's see what happens. So for the hydrogen, 4 grams of hydrogen can make 36 grams of water. 8 grams of oxygen can only make 9 grams of water. Well, you would have been right. And the reason I threw this one out, the reason I put this one in, because I wanted people to notice that even though the masses might be in that 1 to 2 ratio, the answer to the question is not. So, how are we doing so far? Now here's one for you to try on your own. Here's the balance equation. You always need a balance equation. So pause, try this one out. Now let's see how you did. Come on back and see the solution. Okay, here we go. I write my two questions. Now for this first one, do this first. I'm going to need the molar mass of BaO. There's only 1 mole of it here. And there's only 1 mole of hydrogen peroxide. That'll be pretty straightforward then. Okay, barium oxide. That's a molar mass. I could make a pretty small number, 0.301 grams. What if all my HCl was going to react? I could make slightly more. Therefore, which one of these two is the most I can make? It's got to be the smaller one. How did you do? These are the most difficult questions you're going to see in the chapter by far. And for some of you, they might be the more difficult ones you'll see all semester. Next thing we want to check out is theoretical yield versus actual yield. The theoretical yield is what you've been finding so far in this presentation. The theoretical yield is the most you can ever make in a chemical reaction. Now, we don't expect to make the theoretical yield. We hope we do, and that would be great if we could, but there's always going to be some waste. So we hope for a number that's close to the theoretical yield, and that's called the actual yield, what we really wind up making. So the actual yield is determined through experimentation. The theoretical yield is determined with a balanced equation and molar masses. Now we take both of these and we combine them together to determine a percentage yield. And percentage yield gives us a good way of knowing how well our process has been. Now to calculate a percentage yield, we take the actual yield times 100 and divide by the theoretical yield. We always like to get at least an 80% yield. Now the opposite of percent yield would be percent error. So if you had an 80% yield, that would be a 20% error. So you want a very small error, but a high yield. Now here's a question. Let's say we start off with a mixture of 68.5 grams of carbon monoxide with 18.6 grams of hydrogen. Here's our balanced equation. What is the theoretical yield of methanol? It's methanol right here. Now asking for the theoretical yield is the same thing as saying how many grams of methanol can you make? So we've already been doing these kind of questions. So I'd like you to solve this one and then answer this other question. If the actual yield were 55.7 grams, what is the percent yield? So stop at this point in time, take out a piece of paper, and see how well you can do. The next slide will contain the solution. Here's our equation. Here are our two questions. For the 18.6 grams of hydrogen, we could make 149 grams of methanol. For the carbon monoxide, reacting completely, we can make, looks like almost half. So therefore, the 78.3 grams is the theoretical yield. That's the most we can make. For our percentage yield, we're going to take the actual divided by the theoretical, and we get a percent yield of 71.1%. Right? Pretty straightforward. Now here's one for you to try. Let's see if you can figure this one out. A chemical reaction was performed with the theoretical yield of a product was 29.7 grams. So you're already being given the theoretical yield. This represents only a 65% yield. That's my percent yield. What was the actual yield? Remember, that's your formula. Now see if you can figure this one out on your own. And if you're not sure, if you want to see the solution, just click. So substituting in the data, X in for the actual, theoretical, percent. Next we want to try to solve this finally for X. So now we'd multiply both sides by 29.7. 29.7 would cancel out down here, it winds up here. And I divide both sides by 100. And finally I get this, and that then is my actual yield. So that's one way I can use this formula in some questions. Okay, we're coming up to the end. Well, here's a problem for you to try now that will involve percentage yield as well as some stoichiometry. Potassium chlorate, when heated, will decompose into potassium chloride and oxygen gas. You can see that in the equation. A student performed this experiment using 12.26 grams of potassium chlorate. What was the theoretical yield in grams of oxygen? The actual yield was 4.20 grams. What was the percent yield? Now this is not a limiting reactant question because there's only one reactant. So how will we solve this one? Why don't you stop at this point and try it on your own, and then come back and see the solution. Okay, here's the solution. First thing we need is the question, and that's it. Now in our solution, we're going to have to look up the molar mass of KClO3 and oxygen. So that we know we're going to need to go up here, use the 2 in the molar mass. That's going to put that down here. And the 3O2 would go up on top here. So figure out the molar masses and plug them in, and this is what we would get. You can see the 3 and the 2 from the equation. Here are the molar masses. So this represents the theoretical amount of oxygen that we could make. That's our theoretical yield. You can't make any more than that. As you notice from the question, we made less, 4.20. So now the question becomes, what's the percentage yield then? So we just take our formula and plug in our numbers. And you see we get an 87.5% yield. So how did you do? I hope you did okay. So this is the end of the tutorial.